Okay, chapter 13, integration. This relates to exercise 13b. It's very similar to what we did in 13a, just with a few tweaks or a few bits added on. Now I mentioned that integration is the opposite of differentiation. So if you differentiate the function, you get the differential. If you integrate that differential, you get back to your function. Bearing in mind, of course, we need to have a plus c on the end. As I also mentioned in this chapter, that integrating isn't just undoing a differential. It's not just getting back from the gradient function to the function itself. What it can also do is give you the area underneath a curve. And it does it by adding up all the thin strips underneath the curve, rather like the trapezium rule that some of you may have seen in year 11. And for that reason, it has this S, this long S in front of it, the integral sign. Leibniz actually came up with this, as you may well know. So this means I'm integrating this function, which could mean I'm working out the area underneath this curve. Now at the moment I'm not telling you between which values. So this will be a curve, and if you want the area underneath it, well, I need to tell you between x is 3 and x is 7 or something like that. But as I'm not telling you, it's an indefinite integral. Later on we'll look at definite integrals where I tell you what the two values are that you're integrating between. But for now, let's just get used to the process. So this means I'm integrating this function. We need to have this on the end, a dx, because this means I'm integrating with respect to x. You will come across questions where you're integrating with respect to time, to t, or it could be theta. Just think about it. If you are looking at some mechanics questions and you're looking at velocity over time, then this axis down here is not x, it's t. So you need to specify what you're integrating with respect to. Now at A-level maths, you're really only going to have one variable in here, but later on, if you follow maths beyond A-level or you're doing further maths, you'll come across expressions where you have 2 or 3 variables here, and you need to know what you're integrating with respect to. So you need to have a dx on the end. Okay, so let's deal with this. We're going to follow the usual procedure. We're going to increase the power by 1. So half plus 1 is 3 over 2. We're much happier writing powers as top heavy or vulgar fractions if that's necessary. So increase the power by 1 and divide by the new power. We'll sort that out in a minute. Plus increase the power by 1, x to the power 4, there's my 2, divide by the new power. Must have a plus c on the end. Okay, let's simplify this a bit. Divide by 3 divided by 2, so that's going to be 2x to the 3 over 2. Sorry, over 3, 2x to the 3 over 2 over 3, plus x to the power 4 over 2. 2 over 4 is the same as divide by 2, plus c. And that would be your answer. Like I said, later on we're going to be substituting some values of x in here. So if you wanted to work out the area of this curve between x is 1 and 6, then you'd put 1 and 6 in here. But we'll look at those later on. Right, let's look at a second example. This one was quite straightforward because I've written it as separate pieces, separate bits, so I can deal with each individually. Here, I think I've got some working out to do first. This bit here is particularly awkward. I've got x's on top and a constant on top, and there's more x's on the bottom. I want to try and rewrite this as separate polynomial functions, which is much easier to integrate. In fact, in integration generally throughout year 12 and year 13, the hardest bit is often writing the function you're trying to integrate into an easy way, into an easy form, before you can actually integrate. Right, well, I need to tidy this up first because this is a mess. Okay, let's get rid of that squared. So let's 2 squared is 4, x squared there. Right. This bit here also needs tidying up. I'm going to separate this into 2 separate fractions, and I'm going to write this not using a square root sign but using a power. It's much easier to integrate if we've got roots, cube roots, square roots, and so on written as powers. So this bit is x to the power half over x squared plus 5 over x squared dx. Okay, it's getting there, but this is still a bit messy, or at least it's a bit tricky to integrate this as it is. So I'm going to simplify it further. The 4x squared, that's quite easy. Thinking back to year 9 maybe, the second rule of indices, if I'm dividing two values, or dividing a value with powers, then you just take away the powers. So I've got half, take away 2, will be minus 1.5. So that's going to be plus x to the minus 1.5. Much happier writing it as minus 3 over 2. And the divide by x squared is the same as 5x to the minus 2. That's much easier to deal with. And now I just apply the rules, the process that I've learned for integration. Increase the power by 1. Divide by the new power. Increase the power by 1, so that's going to be minus 1/2. Divide by the new power. Increase the power by 1. Divide by the new power. And now I've just integrated it, so I must put a plus c on the end. This can be simplified, it can be tidied up. So let's just wrap this up. 4/3 x cubed. Now look at these two. You can either write it like this, with the x next to the 4 on top of the fraction, or write it as 4/3 x cubed. It doesn't matter, so long as your working is very clear. If you get a bit scruffy and you write 4/3 on the top line here, then it could be construed as being 4/3x cubed. So make sure if you're going to write like this that you write it clearly as a fraction in front and this x cubed is on top. Okay, divided by 1/2 is the same as times by 2, and you've got a minus here, so it's minus 2x to the minus 1/2, and we've got a minus there, minus 5x to the minus 1 plus c. You may well see this written as 2 over root x, so get used to that, and this could be written as 5 over x, of course, assuming you know your negative powers.